Hi everyone. So we have just seen race condition. Now I would like to introduce a very simple term to you. So I'm introducing it because it will be used very often. It's called as critical section. So you might have heard of it while learning about operating systems. What is critical section? Critical section is nothing but it is a piece of code which can indulge into race conditions. For example, here in our entire program, this one-liner is what our critical section is. So what is the meaning of making your code thread safe? It means so many things, but one of the things that it means is to guard your critical sections, to make sure that your critical sections do not actually indulge in race conditions. Now guys, before we learn about the sure short way to handle race conditions, let me tell you that when I had run this program so many times, probably by lessening the number of iterations, we were lucky not to encounter race conditions sometimes. So if you remember, when I had changed the value of number of iterations to something small, let's say if I even change it right now to 10, and then if I run this program, then my expectation will be to see 20 as the output, right? And it'll happen that sometimes I'll actually see 20, like now, I can see 20. So here I was able to see 20 because I was lucky. The number of iterations were few and never ever it happened that the threads got scheduled in a manner where race condition could actually happen. So guys, if you try to understand when does race condition happen, you will automatically get an answer to how to probably avoid it. So guys, let's look at this mode of or this pattern of sequencing the threads. So here thread 1 had fetched the value of x to be 5. Okay. Now during that time, unfortunately a context switch happened and thread 2 also found that value out to be 5. But do you know this 5 is actually a stale value. Why? Because the value of x, which was 5, is in process of updation. Now, before it is updated, if some other threads read it, then they can indulge into race condition scenarios. Okay, now, what if our CPU schedules our threads in a fashion where if a thread has started modifying x, then unless it has modified it completely, other thread cannot begin its journey. If the scheduling is done in this manner, then the race condition will be completely avoided, isn't it? So guys, what I basically mean by that is, let's say the first thread that got scheduled was T1 and it performed a fetch. Now, when it has performed a fetch, let's say a context switch happened. Now, when context switch happened, another thread came, let's say thread 2. Now, this thread 2 should not be allowed to do anything on this X. It should not be allowed to perform a fetch or compute or update, nothing. Yeah, for sure it can perform some other task if it wants, but it cannot touch this X. Okay. Now let's say another context switch happened where T1 again came into picture and T1 this time was able to perform compute as well as update. Now if thread 2 wants, it can get inside and perform a fetch. So basically, if thread 1 is in the middle of fetch, compute, update, during that time, other threads should not be allowed to perform this journey. They should not be allowed to perform any of these fetch, compute, and update. Context switches can keep on happening, okay? But the point is that no other thread should be allowed to execute that critical section unless thread 1 has completely executed it. Now keep it in your mind that thread 1 can execute it in different cycles. I mean, it's not necessary that it has been scheduled once on the CPU core and then it cannot be rescheduled later for the other part of its critical section, which is compute or update. No, it's not necessary. That can very well happen. But the important thing is that when it is in middle of its fetch, compute, and update journey, other threads cannot do any of that. Okay, cool. Now when we have this clarity in our mind, so we would want scheduling to be done in this manner, but we all know that scheduling is not in our hands. We don't control it. It's under the control of CPU scheduler. Okay, so we need to have some other mechanism. Okay, so that other mechanism is basically introduced by some form of locking. So what is this locking? We can basically acquire lock on literally any object. On any object. Let's say for now that object is X. Now, when you acquire lock on an object, then until unless you release that lock, it cannot be acquired by any other thread. Okay, so let's say it is thread 1 which took a lock on X. Okay, now until unless it releases that, thread 2, thread 3 or any other thread cannot acquire a lock. So basically the rule of thumb is that if you have some code which is your critical section, let's say here is your critical section, then in order to execute that critical section, you must first acquire a lock. So you should acquire a lock on X. After that, you should execute your critical section. And once you are done executing your critical section, you must then release that lock on X so that it can now be acquired by some other thread. That is the thumb rule basically. So what does it mean? It means that let's say thread 1 entered inside this increment method, and if the first thing that we do is acquire a lock on X, then it means that no other thread now can acquire that lock until unless the current thread has released it. And when is the current thread going to release it? After executing the critical section. So it means that your critical section, which was composed of 3 different steps, which were fetch, compute, and update, will all be executed for the current thread. Then only the other thread can take it on from there. So this is a very, very standard solution for race conditions, that you acquire a lock and then execute your critical section. Now you can acquire a lock on any object, on any random object. So for example, let's say here I go ahead and create a random object. I'll give it a suitable name. Let's say lock. You can see it's a random object. It can be anything. It can be an instance of your user defined type also. So here I'm just initializing it. This dot lock equals to new of some object. Okay. Now the first thing that I'll do whenever my thread comes inside is to acquire a lock. And in order to acquire a lock, you can use synchronized keyword. So you can say synchronized, and here inside braces, you can specify the object on which you want to acquire the lock. So here our object's name is lock. And then within these braces, you can simply specify your critical section code. And once you are out of these braces, it will naturally release the lock so that then it can be acquired by some other thread. So now basically your program will run in this fashion, that if your thread 1 has gotten inside increment method, it will acquire a lock, perform critical section, and then it will release the lock. And then only some other thread can acquire this lock and do the critical section part. So you can see that here, whatever our critical section is, that cannot be performed concurrently. That is in fact being performed sequentially. So whenever you guard a piece of code by synchronized block, which is by acquiring lock on something, then that means that section of code will be executed sequentially only. Thread 1, if it started, it will complete it in different cycles. Then only some other thread can start it. And when it releases, then only some other thread can take over. So that's the basic idea. Now guys, if I go ahead and run this program, you can see that we are printing 20. Now let's figure out whether this is right output or not. So here it was 10 and there were 2 threads running, so it is 20. Let's make it a bit larger. So for such large iteration, we had seen that the race condition was easily happening, but now it is not happening. You can run it multiple times over and over again, and you will see that the race condition will not happen. Why? Because we have concretely avoided it. Okay, cool. So this is a way to handle race conditions. One more thing. Some people say that, hey, why you have created a different object just for the purpose of acquiring lock? Because if you can acquire lock on any object, why not acquire on the current object itself, which is this? We all know that this keyword refers to the current instance of number store, which was used to invoke this method, right? So if I do away with this object that we had created, that means whenever a thread comes inside, it would take a lock on the instance of number store. Now we know that it's the same instance of number store which is being used by both the threads. Do you remember that? Both the threads were injected with the same instance of number store, right? So it means that when thread 1 has acquired a lock on number store, during that time, thread 2 can't. Okay, so even this thing works perfectly well. You can run this again and again to convince yourself that this logic perfectly works. Okay, one more thing. There is a shortcut for doing this. If you remove this piece of code and just write synchronized over here in this method, basically, if you make the signature of this method as synchronized, it would mean exact same thing which previous code was meaning. So it means whenever a thread comes inside increment method, the first thing it will do is it will acquire lock on the current object, perform everything inside the function as critical section, and then only it would exit out of that. So one way is you have synchronized blocks written inside method. Another way is you mark that method itself as synchronized, but keep it in your mind, when you mark that entire method as synchronized, it means that that entire function is now sequential. I mean, all the logic inside that will now be treated as a critical section, which will be executed sequentially by the threads. So you can run this program also, and you will see that you are getting the exact same output only. Also, one final thing. You might have heard, or you will at least get to hear about this thing called as atomic operations. So whatever we have done right now by making this thing synchronized is nothing but an atomic operation. So now I can see that this increment is atomic in nature. Atomic means that if an operation is composed of multiple steps, like here there were 3 steps: fetch, compute, and update. Now, if you are ensuring that all these 3 steps are first performed by a current thread, then only other thread is able to carry it on, then that means that your operation is atomic by nature. Otherwise, it is not atomic by nature. If you have just performed a fetch and some other thread has started its fetch and compute, then it's not atomic. So you might hear these jargons from people that, hey, if you have some part of your code which is acting as a critical section, which can in future lead to race condition, please make it atomic. And how do you make it atomic? By guarding it with the help of locks. We'll continue talking more about our locks, but this was first intro to the idea of locks.